just for a change, what I'm going to do, I'm going to consider a triangular source. Okay, so Vi is your alternating triangular source with a maximum value of plus or minus 5 volts. Okay, so the positive peak is plus 5 volts and the negative peak of the input is minus 5 volts. And this is where we are interested in finding out the output voltage. Okay, so capacitor. So it's a negative clamper in the sense that the positive half cycle of the input, the capacitor is charged. All right, fine. So since we are talking about a practical diode, so what we have to do is we have to substitute the diode model. Okay, so in figure 2, let us substitute the diode model. Okay. So practical diode is replaced with an ideal diode D and the barrier potential plus minus 0.7 volts. Along with barrier potential, you are supposed to connect the reference DC voltage as well, that is 2 volts. And this is your triangular source. This is RL. Okay. Now, as you can clearly observe that there are 2 DC sources in the diode leg, right? 2 volt external DC source and 0.7 volt, which is the barrier potential of the diode. So, you have to check how these 2 sources are connected to each other. So these 2 sources are connected in additive polarity manner, in the sense minus plus, minus plus. So that is, the 2 sources are sending the current in the same direction, which is called as additive polarity. Hence, what you can do, you can draw a single voltage source with the combined potential. Okay, so what is the combined potential? 2 plus 0.7, that's 2.7. Upper side positive and lower side negative. Okay, so in figure 3, let us draw the practical circuit of the diode. Okay, clamper. Okay, this is your ideal diode and the net potential, net DC potential of the circuit. How much is it? 2.7 volts. All right. So this is RL and this is your alternating triangular source. Okay, so this is figure 3. All right, so now we can go to the analysis part. So first let us talk about the charging cycle. Charging cycle. Okay. So the capacitor is going to get charged in the first positive half cycle. In the positive half cycle. So capacitor C gets charged when the input Vi is greater than 2.7 volts. Quite obvious, right? Because in order to charge the capacitor, the diode should get into conduction. And the conduction is possible only if you have the clockwise direction of current. Okay, so when your input is greater than 2.7 volt, the diode gets forward bias and the capacitor is going to get charged. Okay, so for any voltage, in case if your input voltage is less than 2.7 volt, okay, diode is off and C is not charged. So the capacitor doesn't get charged in case of your input voltage less than 2.7 volts. Okay, fine. So let us assume that the input voltage is greater than the threshold voltage. Okay, so what happens to the equivalent circuit? In the equivalent circuit, what I'm going to do, I'm going to erase this part. So diode should be replaced with a short circuit. Okay. So now you apply the KVL. So this is plus minus because the terminal of the capacitor connected to the source attains the source polarity. So the source is having positive polarity, hence the terminal attains positive polarity, and the opposite terminal will attain the negative polarity. All right, apply KVL in clockwise direction. Apply KVL in clockwise direction. So when you apply KVL, what do you get? Minus to plus VI, plus to minus, hence VC, and plus to minus, that is minus 2.7 is equal to 0. So this is your KVL, okay, equation. And from this equation, you can extract the value of VC. So VC going to be VI minus 2.7 volt. Okay, this is the capacitor voltage. Therefore, when your input attains maximum value, and what is the maximum value of the input? In the very beginning, I have mentioned the specification for the input, right? The maximum value is plus or minus 5 volts. Since we are dealing with the positive half cycle, the maximum value needs to be substituted as plus 5 volts. Okay, so how much you will get the capacitor voltage? VC is equal to 5 minus 2.7. So 5 minus 2.7, okay, gives VC is equal to 2.3 volt. Okay, so you can clearly observe that we have controlled the charging of the capacitor. In case of unbiased clamper, what used to happen is that the capacitor used to get charged to the maximum value of the input. All right, but using biased method, you can control the charging voltage of the capacitor. Okay, so we have limited the capacitor voltage to just 2.3 volts, and this is possible by introducing a DC reference or a biasing technique. All right, so this is what is called as biasing. So using biasing, the user can insert the required amount of DC in the output. All right, so over here you are trying to insert 2.3 volts of DC. Fine. So having known the biasing voltage will enable you to find out the output voltage for a positive half cycle as well as a negative half cycle. All right, so second part of the analysis is your output voltage. Okay, once the capacitor is charged, you can proceed to find the output voltage. So first let us consider, okay, positive half cycle. Positive half cycle. So during positive half cycle, what happens? So let's draw the equivalent circuit first. A triangular source, capacitor, diode, the threshold voltage, which is 2.7 volts, and then the load resistance. This is your input, and this is your output. And please mark the capacitor voltage, okay, with the assigned polarity. So positive half cycle. So in the positive half cycle, you can clearly observe that for VI less than or equal to VI less than or equal to the threshold value, that is 2.7 volt. What happens to diode conduction? This is diode. Okay, whenever your input is less than or equal to 2.7 volt, diode will be in off state. Okay, that's what I was telling in the previous class as well. So whenever the input is less than or equal to 2.7, or input is greater, the diode always it will be in off condition. So diode will be in off condition. So off condition can be shown with an open circuit. Okay, so therefore KVL equation gives okay, this is the direction in which you are supposed to apply KVL. It's VI minus VC minus V0 is equal to 0. That implies V0 is equal to VI minus VC. Okay, so this is your output equation for positive half cycle. Okay, all right. So during positive half cycle, okay, when your input is 0, your output is 0 minus VC. 0 minus VC. Okay. So what is VC? The capacitor voltage, which is 2.3 volts. So it is 0 minus 2.3. It is equal to minus 2.3 volts. So that means to say, when your input is starting from origin, your output starts with the minus 2.3 volts level. On the other hand, when your input reaches the positive maximum value, that is 5 volts, your output is equal to 5 minus 2.3, and that gives 2.7 volt. Okay, so this is the circuit scenario for positive half cycle. Okay, now let us examine the negative half cycle. Okay, so in the negative half cycle also, the diode will be in off state. Okay. Reason I have already explained in the previous class. Invert the polarity for input. Okay, as you can clearly observe that both VI and the reference source, okay, will help each other in reverse biasing the diode. Okay, so both VI and 2.7 volt source will reverse bias the diode. So diode is going to get reverse biased. So reverse biased as in open circuit. Okay, so you can just show an open circuit here. Okay, and you can apply the KVL in the anti-clockwise direction. Okay, so apply KVL in anti-clockwise direction, which gives minus to plus VI, minus to plus V0, and minus to plus VC is equal to 0. That implies output is equal to minus VI minus VC. All right. So the negative sign indicates that the output is reversed. All right. So this is the negative sign. It simply indicates that output is inverted. All right. So let us examine, what will be the, the signal value we are going to get in the negative half cycle. So even in the negative half cycle, when your input is 0, okay, you can expect the output value as 0 minus Vc as minus 2.3 volts as expected, right? Which we have already seen for positive half cycle. On the other hand, when your input reverses its direction in the negative half cycle, that is, when your input attains 5 volts in the negative direction, your output becomes minus Vi, that is 5, minus Vc, that is 2.3, and that becomes minus 7.3 volts. All right. So now that we have the instantaneous values of positive half cycle as well as negative half cycle of the output, we can plot the waveforms. So in the third part, let us plot the waveforms. Fine. So first let me plot the input. Input. Oh, it's a triangular wave, right? Triangular wave. So this is your 0 volt plus 5 volts. This is minus 5 volts. All right, so that's your input. Now let us draw the output. Output. So when you are for the positive half cycle, you see this is your positive half cycle and this is your negative half cycle. So in the positive half cycle, when your input was 0, output was minus 2.3 volts. And when your input was plus 5 volts, output was at plus 2.7 volts. So when your input is 0, output is minus 2.3. So let us consider this as 0 volt level for the output. Minus 2.3 going to be somewhere here. Output is at minus 2.3 volts. And when your input is at plus 5 volt level, what will be the output? Plus 2.7. 2.7. Mark that 2.7. This is plus 2.7. And similarly, when your input falls to 0, the output will be at minus 2.3 volts level. So that's your output for the positive half cycle of the input. Similarly, in the negative half cycle, when your input is 0, output will be at minus 2.3 volts. And when your input becomes 5 volt in the negative direction, your output becomes minus 7.3 volt. 7.3. So this is minus 5 volt. Minus 7.3 will be somewhere here. And once again, when your input falls to 0, the output attains minus 2.3 volt level. So this is your 0 reference. All right, this is your 0 reference. T in the time axis. So this is your input and this is your output. Now, can anyone tell me what is the DC shift in this particular clamping circuit? Can you quickly type your answer? What is the DC shift for this biased negative clamper? Can you quickly type the answer? Minus 2.3. So this is a negative clamper in which the wave is getting pushed down by an amount of minus 2.3 volts. So this is the shift. This is the shift. As you can clearly observe that the wave is getting pushed down. Okay, hence it is negative clamper. Negative clamper. Okay, you can also try drawing its transfer characteristics. Okay. Next, let me write transfer characteristics. Very interesting transfer characteristics. So what I'll do first, I will draw the axis. Okay, and then you can mark the axis V0, Vi, minus Vi, and minus V0. Okay, so during positive half cycle, we know that when your input is 0, output will be at minus 2.3 volts level. So let me mark minus 2.3 volts level. And when your input attains plus 5 volt value, your output will be at what value? Plus 2.7 volt value. So plus 2.7 will be somewhere here. Somewhere here. Okay, so what you have to do is you have to just join a line. Okay. Okay, somewhere here. Okay. And projection you draw on y-axis. So this is plus 2.7 volt. Okay. On the other hand, during the negative half cycle, when your input attains 5 volts in the negative direction, your output attains what value? Minus 7.3 volts value. Okay, minus 7.3 volts. So minus 7.3, probably you can draw something like this. Okay, somewhere here. Yeah. So this is minus 7.3 volts. Okay, fine. So this is your transfer characteristics. Okay. Now I want you to tell me this one. What is a peak-to-peak value? Can anyone quickly type the answer? What is the peak-to-peak value for a clamper circuit? Okay. You have to tell me in this manner. Peak-to-peak of input and V peak-to-peak of output. V peak-to-peak of input and V peak-to-peak of output. Your answers can be separated with a comma. Okay, let's say 5 volt, comma 5 volt, something like that. So the first one is for the input peak-to-peak, and the second one is for the output peak-to-peak. Can you quickly type the answer? What will be the peak-to-peak value? Okay, what do you mean by peak-to-peak? Peak-to-peak means the distance measured from positive maxima to negative maxima. That is this distance. This is your positive maxima, right? And this is your negative maxima. So if you calculate the distance, you will get the peak-to-peak value. So this is your V peak-to-peak of input. What is the peak-to-peak value? 5 minus of minus 5, that is 10 volt. So 10 volt is the peak-to-peak value of the input. And what about the output? Your output will have a different peak-to-peak value. That's the reason I made you to calculate this. Okay. So once again, even for output, the peak-to-peak value is defined as distance traveled from positive peak of the output to the negative peak of the output. So what is the positive peak of the output? Plus 2.7 volt minus, okay, and what is the negative peak of the output? Minus 7.3 volts. So minus of minus 7.3 volts. So how much you'll get? 10 volt. Okay, so this is the feature of a clamper circuit. In case of clamper circuit, the peak-to-peak value will not change. Okay, the peak-to-peak value remains the same. Only the exception is that the wave, either it is getting shifted down or the wave is getting shifted up. Only that's the difference. Okay, so this is very, very important. The appearance of the signal will not change in case of clamper. Can you plot the output waveform? Okay, so what you can do, you can plot the output waveform and you can send a snapshot in the AEC WhatsApp group. Okay, can you quickly try it? Can you try, yes or no? Fine. So, yeah, charging cycle. Charging cycle. Plus minus, you put the polarity. So the capacitor is going to attain polarity as shown in the figure. Okay. So the silicon diode will have a barrier potential. Okay. Of this polarity sense. Okay, that is plus minus, upper side positive and lower side negative. So when you compare Vk with 2 volt DC value, you can clearly observe that there is phase opposition, or the two cells are connected in subtractive manner. And so what you can do is you can replace the two cells with an effective voltage source. Okay, so what is the effective voltage source? 2 minus 0.7, that is 1.3 volts. So the total DC reference is 1.3 volts. Okay, and the capacitor is going to get charged in the positive half cycle. So charging takes place in the first positive half cycle. Okay, so there you are. You can put the direction for applying KVL. So what do you get? Vi minus Vc plus 1.3 is equal to 0, or Vc is equal to Vi plus 1.3 volts. Okay, so this is your KVL equation for the capacitor voltage. So when your input attains maximum value, that is 5 volts, your capacitor gets charged to Vc is equal to 5 plus 1.3, that is 6.3 volts. Okay, so this is the reason why your classmates have typed the answer as 6.3 volts, which is correct. Okay, so when for the output cycle, okay, when we consider, let's say, a positive half cycle, the output cycle, let's consider a positive half cycle. Okay, I will not redraw the circuit. Okay, I assume that you have understood the technique. So positive half cycle, diode is off. That's what I can write. Diode is off. D is off, which is true for all positive clampers and all negative clampers, whether it is biased, unbiased, with ideal diode or with practical diode. Doesn't matter. Whenever you go for checking the output voltage, always you keep your diode in off condition. Okay, so that means to say just you isolate the diode terminals. That's all. Okay, so when diode D is off, you can apply KVL in clockwise direction, which will give you the KVL equation as VI minus VC minus V naught is equal to 0, or you will get V naught is equal to VI minus VC. So this is your KVL equation for positive half cycle. Okay, side by side I will also write the KVL equation for negative half cycle. Okay, negative cycle. Very simple. V naught is equal to, for positive half cycle you will get plus VI. For the negative half cycle you will get minus VI. That's all. Then rest all remains the same. Okay, so this is the KVL equation for negative half cycle. This is called as intuitive analysis. Okay, based on the past knowledge, you can quickly write down the equations for negative half cycle. What are you going to do in the negative half cycle? You know the fact that the waveform is going to change its direction. So just you change the direction. How do you incorporate changes in the direction? By introducing a negative sign. Okay, that's all we need. So in the positive half cycle, when your input is 0, output is minus VC or minus 6.3 volts. And when your input is 5 volts, output is 5 minus 6.3. So that is how much you'll get? Minus 1.3. Okay. Similarly, in the negative half cycle, when your input is 0, output is minus 6.3, and when the input changes its direction, and when it becomes 5 volts in the negative direction, your output becomes minus 5 minus 6.3, or V naught is equal to minus 11.3. Okay, so that's your output. So you know the status of positive half cycle of the output as well as the negative half cycle of the output. So you can quickly draw or plot the waveform. When your input is 0, output is minus 6.3. So minus 6.3 is somewhere here. And when your input is plus 5 volts, your output will be at minus 1.3. Okay, so minus 1.3 is somewhere here. Somewhere here. So just join. Okay, so that's your, this is minus 1.3 volts. And similarly, when your input becomes 0, the output becomes minus 6.3. Okay, so that's for the positive half cycle. And for the negative half cycle, okay, when your input attains 5 volts in the negative direction, your output will be at minus 11.3, right? So somewhere here. Okay, so this voltage is at minus 11.3. Okay, so that's your output. And peak-to-peak value, if you want to calculate, okay, so you can calculate in this manner. V naught peak-to-peak is equal to the positive peak, which is minus 1.3, minus the negative peak, that is minus 11.3. Okay, so 1.3 plus 11.3, that is 10 volts. Okay, so this is your output for the negative clamper.